presenter is Harald Alverstrand. Harald is working for Cisco, but he's also the chairman of the IETF chairman of IETF. Yes. So he will talk about what is happening in the IETF arena on IPv6. Harald?
Morning, everyone. That's better sound. Yeah. So, how many people don't know how IPv6 works? Nobody dares to admit that. How many are sure they know how IPv6 works? One man, brave man. Great. Okay. I'm going to talk something about IPv6, present changes, and a little bit about the past and the future. IPv6 is only one of the things that the IETF does. We do other minor things like routing protocols, like management protocols, like applications, like a lot of stuff. But IPv6 has certainly been one of the front page topics for a while. This fall it will actually be 10 years since the IETF made a decision on what IPv6 should look like. Basically, take IPv4, make bigger addresses, and polish up some really bad parts and then ship it. We thought we could do that very quickly. Okay, 10 years isn't that bad. So, anyway, it seems to work. And the most amazing thing to me about the whole process is that so far there still isn't a credible alternative to v6. If you want an internet, we'd better get this beast on the road, because that's what we got. I'm chair of the IETF, the Internet Engineering Task Force, which means that I'm in charge of the whole kit and caboodle. And one of the things I'm in charge of is managing the people who manage the people who manage the people who actually write specs for IPv6. I'm a bit high up a food chain, which means that I might miss the occasional detail. Like if you ask me which of the bits in the diffserv field actually is stolen by ECN, I couldn't tell you if it was left or the right bit. But there are two. Anyway, this is a status update. High-level issues, high-level questions, high-level answers. You're supposed to be a little bit worried and confused by the end of the presentation, so you'll need to ask questions. So, if you figure out that you have no idea what I'm talking about, or that this surely must be wrong, please do ask questions. That's the only way you'll get answers from me. Okay, overview, what I'm going to tell you. IPv6 is solid, stable, and useful. There are lots of other specs that are using IPv6 for various other purposes, including some things that are really, really hard to do when you're running IPv4. But in spite of this being solid, stable, and useful, it really ain't going to change on you. There are a number of things that are mildly to severely controversial. And since the IETF is a consensus organization, we do a lot of fighting. That's what consensus is all about. Discussing in the open until you actually agree on something. Takes a lot of time, though. Basic IPv6. Big secret, it's IPv4 with bigger addresses. That has the good thing that once you've committed yourself to it, converting to IPv6 is pretty easy. Just make sure you don't assume the size of addresses fits inside an int. Work on your dependencies and code, and it's mostly easy, especially if you bother to write down what you're doing. I'm told that no IPv6 presentation should ever be without its own slide on the IPv6 header format, so I put this one in. This is the magic of IPv6. Has anyone not seen this one before? Thought so. Just about. We fiddle a little bit with the labels and so on, but mainly this is what was decided 10 years ago, and we still haven't gotten a better suggestion. It works. Stuff that works. You can download the slide and read it all. I won't bother. Lots of stuff that just works. There are a few things that are just about rolling out the door. DHCP v6, which I regard as an excellent tool for configuring v6 nodes, as long as you don't use it for assigning addresses, which puts me squarely in the middle of both camps on v6 auto configuration, which means that everyone can be mad at me. That's wonderful. Mobile IPv6, just about the same thing as a mobile IPv4, but a little cleaner. We eliminated one entity from the diagram, and we added a little more security, added a little more things to avoid triangular routing. So it might be a little better than mobile IPv4, but just about the same principles. It's in front of the ISG just about now, with a few remaining issues that the working group has just sorted out, but reasonably stable. A sea change in the way the IETF works over the last couple of years has been that we now routinely assume that any other spec has to deal with IPv6. If you send something for approval that says, okay, this works on IPv4, we don't care about anything else. That's got to be justified. So most specs now come up with v6 as part of the basic package. And a lot of work is being done on what are we actually going to use this stuff for, and how are we going to use it? How is it going to impact us? Like the 3GPP folks, which I claim is the only deployment group that seriously knows that they have to count to 1 billion. That's mobile phone people. And the scenarios group, I'll return to that. The other interesting part is that v6 is getting out in the real world. Major vendors and lots of minor vendors routinely ship v6-enabled products. If you take your Windows XP SP1 box and connect it to a network that runs IPv6, you should look at the interface configuration, but because it will run IPv6 for you. And Microsoft shipped this funny thing called 3 degrees, which is a kind of shared mindshare application. The thing that is not put on the front page, or the marketing literature for this, is that it's actually a v6 testbed. So far, the biggest so far, and they ship this to people without making them aware that by doing this, they're running IPv6, and it works. In fact, one of the more severe problems has been that if you put it into an existing and badly configured IPv6 network, you get trouble. Now, that's what I call failure caused by success, which I much prefer to failure caused by failure. And of course, if you need IPv6 addresses for real, just ask. You'll get them. But that was the good news. There are still some fights going on. And since the rumor mill and press love fights, they're like much more interesting, make much more interesting stories than just everything's working and it's just useful. There is some stuff in the IPv6 specification where there are wide parts of the community that don't like it. And some of it is just broken and we should remove it. But at the same time, some people have made commitments to deliver products that are based on features that are badly designed and haven't yet discovered that it's so broken that they better find another way to do it. So the process ain't pretty. That's what consensus is all about. Let's get a fight into the open. There's some details that just needed fixing. Like, we decided 2 years ago that we had this simple way to put IPv6 addresses into the DNS and a more complicated way to do it. And when we worked through the complications of the complicated way, several people were horrified enough that they suggested we shouldn't do it. So it took a while until that decision got documented. RFC 3363 does it. We made an error in the initial address architecture document, which says that there exists such a thing as a top-level aggregation of which there can be no more than 8,000 odd in the world. That was just stupid. So we republished the address architecture and removed the concept. It's no longer there. This particular publication got delayed for about 6 months because we had some controversies about a few issues, especially whether or not there's something magic about the 64-bit boundary in the middle of the address. I think the magic is now firmly embedded. There's no way we're getting rid of it. We might regret it, but we're not getting rid of it. So, but now for the real bloody mess, site local. Site local is the concept that if you have, there are 3 buttons on this thing I should push at various times, and I do get them confused. So, if you have a network, or a set of networks, which is a site, you can assign addresses under FEC0 ... without any regard for what other sites might do. So, you can assign a machine the number 1. If you have another site, you can do the same thing. Now, this guy is caught in the middle. He's connected to both. So he's a site border entity. So he has to say that if a packet comes in with this address on this interface, it's going to be handled differently from a packet coming in from this address on this interface. And in particular, if a packet comes in from a third node, and you need to forward it to this one, you must not forward it to that one. So it needs to enforce boundaries. And people were saying that this was a very good thing because it allowed you a very simple and very specific form of access control. And also, if you take this network here, load it onto a train, and ship it to Ukraine, you don't have to change the addresses of this form, even while it's connecting to every IPv6 network on the way. But there are a few buts. Like, if this box wants to communicate globally, it's got to have another address. And when an application on that box needs to talk to someone, it needs to know, is that guy on my network or a global network? And I have to keep, not only to pick the right destination address, but the right source address in order to talk to him. And of course, this guy is a bit caught in the middle. So once we worked through the implications, it was clear that a lot of people didn't like it, to the tune of, how could you ever imagine getting something that stupid into that architecture? And of course, the other one, how could you ever imagine that you could ever live without such a feature? I mean, that's a style of debate when you get engineers into the same room who actually care about something. Well, there was a fight. There were about 3,000 emails. And lots of people became less good friends than they had been before. But the community has achieved rough consensus that this feature is not useful. And the implications for applications and configurations and routing and so on are so complex that it's simply not worth it. So it's being deprecated. There are a few people who disagree with the consensus, which is their right and their duty, and who post about 20 messages a day saying so. Of course, there are a couple of other people posting 20 messages a day saying, no, nah, yeah, you ain't so. So there's still a little bit of shouting going on. But it's basically a done deal now. This feature has been removed. And more positive in the sense that we added complexity instead of mumble, is the flow label. This field up into the upper right-hand corner of the diagram everyone's seen. We were never very clear about how to use that stuff. And we've been vacillating between, okay, let's make the rules very complicated, make interpretations of particular bits inside this field and so on, and, well, just say that it's a label for a flow, and leave it at that. The current spec is on the small side. It says, okay, it's a flow label. And the most important specific statement in that is that if you haven't seen a packet on this flow for 2 minutes, you can assume that it has gone away, unless someone tells you otherwise. And the working group has requested publication on May 1st for this one, so the working group thinks it's finished with it, and I see no reason to believe otherwise. A little more messy is the area of transition mechanisms. How do you live in a system where some of the nodes are v6, some of the nodes are v4, some of the nodes are v6 but know how to send IPv4 packets by sending them to some gateway place, and some of them are v4 and know how to send packets in v6 by sending them to some gateway place, and so on and so forth. The number of mechanisms actually proposed, implemented, deployed, and tested is slightly staggering. So, I'm giving you a quick preview. Next topic. So, the IETF decided that this approach of just figuring out new mechanisms and then seeing if they worked wasn't really optimal for the internet as a whole. So we took one step back. In the process, shutting down the ng-trans working group and creating the v6ops working group, and focusing on writing down which contexts are we actually planning to deploy. Like, you can be an ISP, you can be an enterprise organization, you can be a home user with where there is nobody in the building who knows how to spell IP and think that TCP is a washing machine or something. Or the cellular scenario, which has its own challenges. So they're working on these 4 documents and saying, okay, we know we have all these mechanisms, but we might need some extensions, so there might be some features that are useless. So could you please not publish them in final form until we got this stuff worked out? So they're working on it. It's been, again, mildly controversial because people like Microsoft, who implemented ISOTAP and ship it as part of Windows Server 2003, think that they deserve accommodation for their effort and a names on an RFC. Well, so yes, it's good that they try. No, we're not going to publish yet. So still a bit of a discussion there. We're also doing some minor detail that nobody hears about unless they care, like SEND, securing neighbor discovery. If you put an IPv6 node on the net, and I don't like you being on the net, I can just send you a few packets saying, no, I got this address. No, I got this address. No, you're not. No, I can steal this address too. And you'll not be able to function. I mean, this is not a new feature. ARP works that way too. But with v6, the installed base is small enough that we actually might be able to design a solution and getting it shipped in useful time. And if we know that there is a security hole saying that this will never become a problem, here is a problem. So we charter a working group. They're looking at the problem. I can't say much more than that. A far worse problem is, okay, I'm a site. I'm buying cheap connectivity from the cable service. But that one goes down 3 times a week, and I can't survive with that. So I want a backup connection. More expensive, but I don't have to use it often. Well, multi-home. Oops. Which address? So if you start publishing the addresses of each individual house in Zagreb in the global routing tables, something is going to break somewhere. In IPv4, we just said this is impossible and made multi-provider, multi-homing very expensive. In IPv6, we might have a fresh look. Of course, after all, we got all these nice address bits that we want to throw away for some reason. So, for instance, the exchange-based address allocation is one idea. But we set up a working group to investigate the possibilities, which promptly disappeared into chaos and discussion for about 2 years. So, recent result, we tried replacing a chair or two. And we got some proposals, some of which are completely brain damaged, and the proponents have been told so in no uncertain terms, which have caused them to be very unhappy and claim that they are being treated unfairly. Okay, they might have a point. After all, the guy who claims they're brain damage has been known to have his own brain damage proposals. So you get the style of the discussion is interesting. Yes? All of them? That's the problem. If I had a real good one that everyone was sure was not brain damaged, the internet would be a great place by tomorrow. For instance, we got this proposal for saying that every square meter on the surface of the Earth has its own /64 or 48 or something. And you can use that address if you happen to own that piece of Earth. Well, now build a routing protocol that will function intelligently on top of that. Exchange-based addressing is a slightly less provocative version of the same idea. You hand out addresses based on where someone is instead of who they buy service from. Of course, you can say, okay, you just get multiple addresses and live with it. So you change the TCP layer so that when you make a connection and one address goes away, you just jump to the other one. It's got certain security problems, for instance, but they might be solvable in theory. Or you could replace the IP layer, say that you have this address and you have location, and they're two different things. There are actually people who claim that with a little thought, mobile IP could be turned into such a separation. After all, the only thing you use the home address of mobile IP for is figuring out where to start asking where he is. Anyway, that's a long discussion, and it might converge at some point. At least we're having a meeting in Vienna. We're having 2 meetings in Vienna for this group. And I certainly hope we'll be able to tone down the style of discussion to a level where we actually can figure out what's the difference between brain damage and just soft in the head. I mean, most of the internet was built by people who were soft in the head. Who could ever believe that they could manage to get it work? So I got hopes. But you know, the outstanding architectural issues in IPv6 aren't really IPv6 specific. I mean, Plato and Socrates have had big fights about the nature of identity. When am I someone and not someone else? And if we're looking for a single one-size-fits-all answer for the network, we might not be surprised if we have some problems defining the question, not to mention the answer. What kind of security do we need, and who pays for the security? We got several cases in any internet of risking tragedy of the commons, that common resources are not accounted for and are therefore regarded as free and overused. The global routing tables are one favorite such resource, while the address space used to be such a resource until we installed the RIRs with the flaming swords in hand guarding the Garden of Eden. So occasionally we do get people to protect the commons, but it's not chiefly a technical process. And of course, when there are trade-offs, who negotiates? And where do we go to get answers? IPv6 didn't create those problems. IPv6 can't solve them. But we're going to have to deal with them every day. Summary. IPv6 is stable, ready to be deployed. It works. You have proven it, guys. IPv6 solves the lack of addresses problem. Solved, period, end of sentence. It doesn't solve all the problems in the world. But it does allow us a little more wiggle room to go around once more and see if we can make a better solution to some old problems this time around. So go use it. It works. Questions? Comments? Oops, sorry. Let's see.
Is there any consensus building up over the issue of interdomain multicast routing? I mean, MBGP, BGMP, and things like that.
At the moment, we have a request before the ISG to publish MBGP as experimental, which is regarded as a documentation of current practice and admitting that this is not good enough and we don't know how to make it good enough. I don't see any consensus at the moment towards anything that seems workable. We seem to agree that interdomain multicast routing is a hard problem, and it's one of those that isn't getting easier. So if you have a wonderful new solution that actually works, you might be able to sell it. Because the current contenders sure ain't doing that good.
I would like to ask a couple of questions. First of all, in my opinion, no killer application means no deployment. What is the IPv6 killer application at the moment? Question number one. Question number two is, is IPv6 going to be deployed only in the core network or also at desktop?
Well, to answer question number one, who needs killer applications anyway? No, the real thing that is solved by IPv6 is the fact that people with cheap connections couldn't deploy service. So this enables peer-to-peer networks, IP telephony, and the 3 degrees Microsoft advertising. IPv6 is an enabling technology, and some of the applications we currently have, including widespread web server deployment, IP telephony, and peer-to-peer networking, are very, very much easier on IPv6 than on IPv4. That was the first question. What was the second question again? Okay, the core edge question. Microsoft answered that when they shipped XP. The IPv6 ready boxes are going to be all over the place, at the edges, on the desktops. And when the customers find it in the best interest of to use that readiness and are willing to pay the ISP for it, the core will become IPv6 enabled. So I think deployment will be tried by people like the NRNs. It will be driven by the end user. And once the bit flips, it will be very rapidly rolled out in ISP space. My thinking. I mean, an ISP cannot sell any service for which it doesn't have customers. So the edge has to be there before the core is a paying proposition.
Yeah, but you see, one question is because I have several years I have IPv6. But if I go into the control panel, okay, the only thing it asks is an IPv4 address. So IPv6 is everywhere. But the question is, why do I have to use it?
Well, are you sure it's not just working?
No.
I mean, you should. Unless you have turned off address auto configuration, there's absolutely no reason to ask you for an IPv4 address. It should just work. IPv6 address, sorry. I'm sure that there's someone in the room who can convince your Apple to tell you whether the IPv6 is on or off, but I cannot do that. Sorry.
I have a comment on your question. I think IPv6 is kind of service that you can use and you can solve some kind of problem. So you cannot request killer application from IPv6. It enables you to do something more effectively, more efficiently, if you want. If you don't use, you lose that possibility. That's all. And if the ISP can find out how can they reduce their cost, providing IPv6 service or providing IPv6 solution, then they can provide you IPv6 service, IPv6 only service if they want. And I think that will be a step forward deploying IPv6.
There's a question from Tim Chown, who is watching remotely, and he asks, what can be learnt by commercial networks from research network deployment of IPv6? He notes that we have version 6 on Giant in many NRENs and in some universities.
Well, I think the NRNs are serving a very valuable purpose here. The standard dialogue between a vendor and a provider goes something like, vendor says, is this service useful? And provider says, sure, it's in our products. Vendor and service provider says, but has anyone tried it? And the vendor says, yeah, sure, we tried it in the lab. And instead, the NRNs, are giving us the chance of seeing, instead of this dialogue, we want to try IPv6. Okay, try it. Hey, all the routers crash. Oh, sorry. We'll fix that. Now it works. Oh, that's a little bug. Okay, we'll fix that too. Now, this is when it works, of course. It doesn't always work that way. And after a while, it becomes, the commercial customer comes along and says, hey, I want to run IPv6. And the vendor says, sure, here. And the customer says, but who's tried it? These people and these people and these people and these people. And they all say, hallelujah. Okay, I'll sign. So being first on the market to actually try something for real is a very, very, very valuable service to the internet. Because it's a necessary first thing, which makes the next step of getting support from everyone, everywhere, much, much, much easier.
Any more questions? Thank you, Harald, for this constructive explanation. This is the first applause today, so you should be happy. Huh? So I would like to invite the next speaker, which is Ladislav Lotka from Chestnut, and he will talk about a PC-based IP router developed by yourself, I believe.
I will try to. Yeah, that's no problem. Okay. Oh, which one? Okay, thanks. Fine. So, good morning. I'm going to talk about the LibreRouter project, which is a part of the 6net Work Package 3. And the aim of the project is to develop a high-performance, dual-stack, and truly open router platform based on a commodity PC architecture. And this paper is co-authored by myself and my colleague Jiří Novotný from Masaryk University, Brno. Actually, part of our motivation stems really from a plain curiosity, since I'm sure many of you have been wondering from time to time how the wonderful algorithms in router ASICs and router software are really implemented. And since our friendly router vendors are not really keen on giving out this information, we decided just, okay, let's start with a clean slate and try to implement everything just by ourselves and solve all the problems along the way. And it really turns out to be very interesting research project, and in fact, it's much more work, much more difficult than we expected at first. But we also want our results to be useful, so we think it could be a flexible, open platform for network research, especially in new developing areas like IPv6, where you need to develop new protocols, and it's sometimes a bit complicated to convince the vendors again to implement those protocols. And perhaps it could also serve as a solution for production networks, especially at the network edge, not probably at the network core. And it could also perform quite a number of different special functions like hardware encryption or network monitoring, traffic generation, or perhaps even more exotic functions like audio or video codecs, or even more exotic areas like active networks and so on and so forth. We started from the commodity PC architecture, and we are developing some additional hardware. Perhaps we could also go in the direction of embedded systems, which is not too difficult to do from the current stage. And this project gets financial support from CESNET and the 6NET project. Oops. Oh. Sorry. So speaking about PC router, let's start from the pure software solution. In fact, such routers have been in use in CESNET networks since 1991, 1992. First, we started with operating special purpose operating systems like KA9Q, maybe some of you still remember those, or PC route. And later, we moved over to generic operating systems like different variants of BSD systems, or later Linux. And we used routing software packages like GateD and more recently Zebra. In general, the experience was quite good with these PC routers, and they are still in heavy use in few metropolitan networks. For example, the Brno metropolitan network still uses some 60 PC routers for connecting their schools and student dorms and other facilities. We have some PC routers in our IPv6 national backbone, and by the way, Stick will talk later about M6 network, and this network is still based on FreeBSD PC routers. Speaking about deficiencies of this platform, first is somewhat limited forwarding performance, which is due to some limitations of the PCI and memory buses, and perhaps also due to the number of interrupts that can be serviced. And another problem is with the configuration of Unix boxes. Of course, many Unix gurus are fond of this way of configuring their boxes, but spoiled network administrators usually don't like to fiddle with all those files, init scripts, and so on. So for them, it's really crucial to have an integrated configuration and monitoring environment like the commercial routers have these days. Again, just to give you a view of the forwarding performance of software PCs without any hardware acceleration, it's not too bad. In fact, in these figures, you can see it compared to the performance of Cisco 7500 platform with gigabit Ethernet interfaces. So you can see for large packets, the PC is even gives you higher performance. But with smaller packets, the Cisco 7500 is able to cope with approximately the same number of throughput, and it behaves more gracefully when faced to overloaded situation of an overload. So so it's quite impressive, I would say, but still it's on a gigabit Ethernet. You can only reach, say, in this mixed distribution of packet sizes, you can reach to about 350 megabits per second, which is, of course, not enough for a gigabit Ethernet interface. So after doing this analysis, we decided to go forward in two development directions. One of them is hardware development, and the group of hardware developers is led by my colleague Jura Novotný, and then to create a powerful and user-friendly configuration system. As far as the hardware accelerator is concerned, again, we would like to start with a commodity PC with NetBSD or Linux operating systems, and the development works deals with a field programmable gate array based solution, which means basically that the data plane is going to be handled in the hardware, in the FPGA based board, and control plane and statistics and download of the firmware to the board will be handled in software and through the PCI bus. Our target throughput is about 10 gigabit per second currently, but as the performance of the FPGAs is still growing, we may go even higher. And our idea is to build a quite complicated motherboard for doing this hardware acceleration, and then to add daughter interface card, which are much more easy to develop, and so these can be used interchangeably with the basic motherboard in order to provide gigabit Ethernet interfaces, 10 gig interfaces, and perhaps later packet over SONET. And the configuration system, we decided to base it upon XML data format. And the basic idea is to provide bidirectional translation between this inner XML format and the standard native configuration languages, like those Unix files, or for other purposes, iOS configuration or Juno's configuration. And so at first just to the translation, and later perhaps concentrate on the mechanism how to transfer those configurations between the router and the configuring station. Now, this is our first hardware result. So this is the FPGA-based board. So you can see actually the FPGA chip here. We also have dynamic RAM there. It can be up to 2 gigabytes. And there is contents addressable memory and static memories. You can see we have just short PCI connector here. It's enough for the time being. And there are also some connectors. So to these connectors you can connect those daughter cards, for instance, for realizing different interface types. And there's another connector which could be used for connecting more cards in a daisy chain way together, or to connect test equipment and so on. So basically the architecture of this motherboard is such that it does not have any processor. So far it could be added quite easily, but there was no need for it so far. And the card is a combination of programmable hardware and standard integrated circuits. So the programmable hardware part is this Xilinx FPGA Vertex 2. And actually, there is a series of those FPGAs with the same pin layout, same footprint, so that they can be used interchangeably depending on your performance needs and so on. And also another type of programmable hardware could be used instead of or along with those big FPGA chips. And as for the standard circuits, we use contents addressable memory and other memory types. Static memory should be here as well. And we use PCI interface chips and, of course, power supplies. And as I said earlier, the idea is to have just exchangeable interface card that can be added as needed to this motherboard and provide a way how to connect test equipment or other devices through an extension connector. Speaking about firmware, it's a bit difficult and tricky area since it's not very common yet to develop firmware as an open source, say. So this area is really plagued with all kinds of traps of intellectual property and so on. So we try as much as possible to avoid those traps, but we are not really fundamental about that. So if we really need to use some intellectual property core, we will probably have to do it. And of course, the VHDL is the standard language for developing firmware, so our developers really use it with all the simulation environment that's available. But this environment is rather expensive, and so we try to provide ways how to enable users to change the behavior of the device. This is done through a concept of so-called nanoprocessors, which are simple processors implemented inside of the FPGA. And these have very simple, just few instructions, and so they can be reprogrammed by a user without any development environment. And so most of the functionality is really implemented as those nanoprocessors. The nanoprocessors are also simulated in software, so in general we use so-called hardware-software co-design, which means that algorithms are first developed in software, just in a normal way, compiled in C, and then their time-critical parts can be moved to hardware as necessary. And our developers also have some support from formal verification group, which is able to prove formally that some parts of the code really work or do not contain any deadlocks and so on. This is just a simplified diagram of packet processing, of data flow inside the hardware. I'm not sure I have enough time to get into any depth in it. But perhaps I'd like to mention that this first part, this is so-called header field extractor, which on one direction just stores the data contents of the packet to DRAM, and this is only taken out from the DRAM at the end of the process. And this HVE block then produces a unified, so-called unified header, which contains all the information that's necessary for doing forwarding and packet filtering decision inside the board. And this is about 440 bits in size. And then this goes to the lookup processor, which actually uses content addressable memory for doing the first part of the decision. But since our content addressable memory has rather long size, but it's still only 272 bits, so we need to do the rest outside of it, so it's done in static RAM.
And this way the decision for forwarding, interface, and perhaps packet filtering actions can be done. And then it goes through the rest to the output packet editor, where the packet gets together, and is sent out of the output interface. So as I said, the development is done for of the system software supporting it is done for NetBSD and Linux. And the idea is again to present the card as a standard 4-port, say, in Ethernet device, so that we can use all the tools and all the daemons that are available for standard Unix systems without any changes. And we also plan to have hardware-supported TCP dump support. So just to show you the general idea of the system software, this is the diagram of it. I'm not going to discuss it. So the current status of this is that 4 of those Combo 6 cards have been manufactured and tested, and their manufacturing price is about 3,500 euros. So far we have, or in very, very short time, we should have an interface card with 4 copper gigabit Ethernet interfaces, and later we want to have optical gigabit Ethernet and later 10 gigabit Ethernet interfaces. Low-level drivers for this Combo 6 card is now available for NetBSD and Linux, so that the firmware can really be downloaded to the card. And we have several development tools for controlling the card and even doing some statistical scripts and testing some algorithms this way. And of course, the most intensive work now is on the part of development of the firmware and system software. Now, the second part that I will just shortly mention is the configuration system. We call it Netopere, and we designed it as a more general tool than just configuring PC routers. We want it to be a platform-independent environment for configuring large networks. As I said, the internal data format is in XML, and perhaps you have heard about a new IETF group called NetConf. They have similar goals, also XML-based configuration, but their aim is more to develop communication protocol for exchanging those configurations. Not so much they are not really into the data contents of those configurations, and there are several vendors involved, and they simply can't agree upon a common data language for router configurations. So we think our part could be really on this data contents of the configuration. And the general idea is like this. So we have a number of front ends, command line interface, web interface, later perhaps SNMP. Then we could also translate some legacy languages like Junos or Cisco IOS. And we are also working on something which is called meta configuration, which just aims at configuring the entire network on a higher level, so that then the individual configurations of individual routers are automatically produced from this meta configuration layer. In the middle, we have that XML configuration data repository with version control and so on. And this configuration can be downloaded to the routers either by configuration files or via SNMP, or perhaps with some remote procedure call mechanism. the current status is we agreed upon a preliminary XML schema based on DTD, which covers interface configuration, packet and route filtering, static routes, and RIP and RIP-NG protocols, just to have something to work upon. And we now have Cisco iOS front ends and Junos front ends and a preliminary version of a web front end, so that, for example, we are now able to translate large parts of Cisco, say, Junos configuration to Cisco configuration through the backends also, which are based on the XSLT transformation. And so, as I said, we have a backend for Cisco iOS and also for the Unix systems we need. Yeah, and just finishing. So, if you want to learn more about this project, you are welcome to visit our project site. We are currently working on the contents of that site, but still you can get most of the important information there in the form of technical reports. Actually, as I said, it's going to be an open project, so all our files or all our source code is, including VHDL, is available through the CVS that's also accessible from that site. We have about 5 mailing lists. So we are, again, welcome to join those mailing lists. The project team is rather big, but, well, we have 45 members, including about 25 students. But still, as I said, it's a lot of work, so we would be grateful to anyone who would like to contribute by commenting or even contributing some code to the project. That's about it. Thank you very much. So if you have any questions, I or my colleague. Yes?
A question about this XML configuration sharing stuff. Is there a relationship between this and the netconf stuff going on in the ITF?
Well, as I said, I have exchanged emails with Andy Bierman from Cisco, who is supposed to be chair of this group, I think. And actually, we agreed upon that, what I said, that that netconf group is more involved in defining the communication protocol between the router and the configuring station. And he was also quite open in that he said that it's not possible simply to make the vendors agree upon any configuration languages, and a configuration language including all the knobs for tuning BGP and things like that. So they, on purpose, just left this part out so far, and he actually proposed that perhaps a new group can be founded in IETF dealing with this data contents of the configuration. So that's.
Thank you.
No more questions? Thanks, Ladislav.
Thank you very much.
So I would like to announce the next speaker. It's Stig Benaas from Uninet, and Stig will talk about the grid technology and positioning, and grid positioning in an IPv6 environment.
I'll try to make this short since you probably want to go for lunch in time. So. But yeah, yeah, that's one. Yeah. Okay, so yeah, the original speaker couldn't make it here, so I'm more or less presenting this on behalf of UCL. Next. Okay, So I'll say a few words about why IPv6 is useful to Grid and what UCL have been doing with IPv6 and Grid. So Grid is, well, I think of it mainly as distributed computing. The people most interested in Grid are perhaps the supercomputing people and some scientific users that need a lot of computation power, but distributed computing can be useful in quite a few ways, and I think of Grid as just as much as supercomputing as distributed computing, where you want to access any network services as transparently as possible. And yeah, there's a lot of interest in Grid these days, and you probably heard a Grid presentation in the plenary yesterday. So why do we really bother with IPv6 for Grid? IPv6 has some enhancements compared to IPv4. There are some, well, quite a lot of the features in IPv6 are also in IPv4, but they are as options and not as standard. And there are some small enhancements in IPv6. The really big difference is the address space. And with 128-bit addresses, we can have a globally unique address for every device on the internet. Of course, if you want to do massive distributed computing, you at least want to be able to address all the devices that are to take part in the distributed computing or processing or whatever. And you can actually have many addresses per device if you like. You can have sort of virtual computers or address individual components or sensor or something in a device, or many possibilities. And well, it's a bit controversial, but it looks like you more or less are going ahead towards having 64 bits for location, sort of the routing, and 64 bits for the ID. So you can, sort of have 64 bits for the ID of the device, and you can, for instance, there are some ways of constructing an address from a certificate, for instance, so you can bind an identifier to a certificate, which can be quite useful. And you can move around to different networks and keep the same 64 bits as the ID, which might be useful. But the really big difference is that you can avoid NATs, because the way NATs work, you more or less separate computers into either clients or servers. If you're behind a NAT, you can only be a client. No one else can reach you. And to do distributed computing, you really want all the devices to be able to contact each other, not just in one direction. And so that's really useful. And you also have much more freedom for application protocols. You don't need to, with NATs, you can't really embed addresses or ports in the application protocol, for instance. And might also be other things that you can do more freely without having to care about NATs. One problem, of course, is that you might end up with some hosts that are IPv6 only and some are IPv4 only, and how are they supposed to reach each other? So that's a really big problem. Well, hopefully we get people to move to IPv6 quickly, but well, we'll see. I think I'll skip this slide. Some more improvements with IPv6. And some others. One thing that hasn't been mentioned today, I think, is you also have some work on anycast for IPv6. You can have more or less a group of devices, and you have a way to address just one device in the group. It's very useful if you don't care which device you want to reach, but you really want to reach one of them. Well, not sure if people know that much about how to use it yet, but there are some possibilities. Okay. Then I'll say a few words about Globus. UCL and also University of Southampton and I think some others have been doing some work porting Globus to IPv6. Globus is the grid tool and it's one of the perhaps most important software solutions for grid at the moment. There was something called Grid Toolkit 2, or Globus Toolkit 2, that UCL and Southampton started porting. And, well, they were making quite good progress, but now there's a version 3 out using Java. It's basically written from scratch using very different technologies, so the porting has also started from scratch again. But the new one is written in Java, and when you use Java, you can actually write code that doesn't really care much about the underlying addresses. So most of the toolkit actually works just fine. You just change to a JDK that has IPv6 support, and magically a lot of things work. But, well, there are still some possible problems. So, yeah, what's going on now is actually the underlying topics, I think, or items are already done. And, well, it's been tested with new JDK with IPv6. There's still more work necessary to test that actually everything works. It's a pretty large software, so it's not that easy to make sure that all the different ways of using it actually work with IPv6. There's also some other software like databases and so on that Grid uses, and for instance PostgreSQL, something like that, is ported to IPv6, and you need to use Tomcat with IPv6, and that seems to work. And there's also some work on some other parts of the open grid services architecture that needs to be looked into. There are some parts that are not written in Java, like grid FTP, for instance. Yeah, and for some of these things, you need to go through and see where IPv4 is used and port it and check that it still works with IPv6 and so on. Yeah, and since Globus is still a moving target, they have to check on what's going on, and as soon as there are changes, also incorporate those changes in the IPv6 patches. Yeah, I think that's the most important. Actually, the open grid services architecture is it's an architecture that is used for building, for instance, Globus, that can be used for building a lot of different applications. What it does is more or less give an abstract way of accessing a lot of different devices. And using this, you can build a lot of other tools, like, for instance, UCL has some high-level media gateways that perhaps could use this grid or, OGSA architecture. Yeah. So, yeah, that's what I had.
Any questions? Okay, then. Oh, sorry. Yeah.
Did you try some other grid system for porting IPv6? Or somebody? Do you know,
you mean
SunGrid Engine or Condor or something like that?
No, I have no idea. Sorry. Yeah.
Okay, thank you.
No more? Thank you, Stig. One more presentation before lunch from Viktor Projic from Poland. Viktor will talk about the management of an IPv6 network with IPv4 and IPv6 SNMP gateway.
Yes, that's it. My name is Viktor Prosek. I am come from Poland, and I work in Poznań Supercomputing and Networking Center. I'd like to present part of our contribution to 6net project, Work Package 6, Network Management, Architecture and Tools. A few facts that were mentioned today, but I will emphasize a few of them. IPv6 is known since January 1995. It becomes to be more and more popular service, and to meet users' needs, IPv6 networks have to be managed. But there is no support for IPv6 in commercial management platform. At the moment, we know no one management platform supporting IPv6. Here is the list most known and sophisticated management platforms. It includes HP OpenView, Tivoli NetView, and Cisco Cisco Works for Cisco routers. And the fourth one maybe is not so popular and known as the previous three previous ones, but it plays important role in development of our tool. I will mention it later. So, if we have no support for IPv6, we can manage networks by this way. This is a solution. Management platform uses only IPv4 stack. All the routers have dual stack. If we assume in this model that if problem occur, it would in both networks, IPv4 and IPv6. First weakness is that we cannot monitor IPv6 only network, and the second problem is that if problem occur and concerns only IPv6 network, we are not aware of the problem. So this is the idea of our tool. The main purpose is to enable IPv4 only management platform to manage, configure IPv6 network. Here is overview. Data are going this way through the transition tool, and to the agent response goes the same way to manager. And this is example of how IPv6 network can be managed using our transition tool. IPv4 network is monitored as usually management station it does. So IPv4 only link, and these routers are monitored using IPv4. On transition tool, we have as many IPv4 addresses as many IPv6 devices we want to monitor. So the message goes to the transition tool on one of the IP addresses, IPv4 addresses, and then goes using IPv6 address to appropriate device, goes the same way. Transition tool is not only the idea, but also a working program. Here is SNMP module, which translates SNMP requests and responses. It uses common for all the modules transition database. Transition database is relation one-to-one addresses, and in this presentation, we describe IPv4 to IPv6 translation, but it can also be done all the directions: IPv6 to IPv6, IPv4 to IPv4, and IPv6 to IPv4. Network management stations uses also ICMP protocol to check availability of the routers. So ping module was added to this tool, and to manage our tool, the GUI interface is available. It can be used through the network using IPv4 or IPv6 protocol. Here is a view of GUI. It's like all the graphical interfaces is user-friendly. We hope so. It's written in Java, so it can be used on every platform. Only on Windows there is problem with IPv6. IPv6 support in Java on Windows platform will be until 1.5 version. And GUI uses our own protocol, but it is ciphered by SSL protocol, and the only authentication is done. At the moment, only one GUI is allowed, and it has full privileges. It can not only view the table, but also modify. And results. As I mentioned, this is working software. First test was to check not only if work is done correctly, but also efficiency. There we have a few IPv4 PCs. They query IPv6 devices simultaneously, and the tests was done also for the second direction from request from IPv6 network to IPv4 network. Here are the results. There is no pointer. This window is clickable, so if you download this presentation, you can check the results. Here is the view from cooperation our tool with management platform. These two windows are HP OpenView, and this is MG MIB browser, and no problems occurred. First implementation, public implementation, was on TF-NGN 2 weeks ago in Poznań. Test network consists of IPv4 network, IPv6 network, transition tool between both networks, and WhatsApp management platform installed on one of IPv4 PCs, but it isn't. It's a view from WhatsApp, and the computer with WhatsApp isn't on this view because it's not monitoring itself. WhatsApp have a web interface, so it can be accessible through the web. In a few days, we are going to make a 6-net network map and to monitor using our transition tool to make available map for all the users. In current form, our transition tool seems to be quite useful, but there is a lot of ideas what can be improved, what can be added. The architecture of this tool is modular, so we are planning to add a DNS module. So it will act as a proxy. Address which are not in translation database will be this module will act as a normal proxy, no changes. But if the address is in the translation table, it will be replaced to appropriate pair. Sixth tunnel is for TCP IP connections. So it will be possible to make connection using Telnet or SSH from IPv4 management station to IPv6 network device. And at the moment, SNMP transition tool doesn't know address of management station, so we have to improve it and to forward traps coming from IPv6 network to IPv4 network management station. Now configuration is possible only using GUI interface, but we plan to add also support for SNMP configuration through the SNMP, and also automatic address configuration. So if we add a pair of addresses to the transition table, the operating system configuration of interface automatically changes. And the biggest problem, MIP conversion. We are doing translation at IP layer. Our tool understands messages and data in upper layers, but there is a lot of problems translating the data. So there will be API. If anybody needs to translate and have the rules for the translation of data, it will be possible. Here is proposed new architecture. Modules marked in black are already developed, implemented. Modules in gray are to be done. And the most important thing from this presentation is this URL address. On this site is the software, is documentation. This presentation is also can be downloaded also from this site, and there are 3 simple steps how to get it. And that's all. Thank you.
Perfect timing. Thank you very much.
Thank you.
Is there any question before we break for lunch? Okay, thank you very much.
Thank you.
We would like to start at 2 o'clock, is that right? So if those who are interested, be back at 2 o'clock, and in the meantime, bon appetit.